This assignment, ecliptic curve cryptography, is implemented using the Weierstrass form of elliptic curves over a finite prime field GFP. Uh, Short Weierstrass form, it is represented by an equation y power 2 equal to x power 3 plus ax plus b. The figure shows the real curve geometry and how chord and tangent lines define the group law. Uh, this project has following this file system. So curves.json stores ecliptic curve parameters in a decimal format. So readme, this file contains instructions how to implement this assignment, and readme2 uh, is the documentation file for implementation of this assignment, and test.py. This file drives this script that loads curves, generates keys, signs, verifies, and drives shared keys. So testpy2, this file is similar to testpy, but these provide private keys. So the file output of testpy, this is output of testpy, this file, and uh, test2 underscore output text is output of this file testpy2. So I'm going to explain the code in elliptic curve .py. In the beginning, there are two imports. There are two libraries are imported. Hash lib, and the purpose of this library is for SHA 256 hashing used by sign verification and shared key derivation. Other one is random, and this library is imported for the generation of random private keys and nonces. This is the at this place we are going to initialize elliptic curve parameters here for coefficients a, b, and members object self a, self b, etc. are created, and they are stored in this parameter, because if that init function will finish, they will still stay. So a is the elliptic curve coefficient, and elliptic curve other coefficient is b. Finite field prime module is p, and base points g on the curve represent as a tuple like gx and gy. Self.n is equal to n order of the base point g, which is the number of points on the curve including the point at infinity. This function here, because there are total 11 functions, so this function checks whether the given point lies on the curve or not. So this code is, if the point is none, it is considered to be at infinity, which is always on the curve. So this part implements the equation which I discussed in the beginning, mathematical equation, that was x square. So this is x square, y square minus x square minus self dot a. This is the code representation of that mathematical equation, algebraic equation, sorry. So def in this function computes the modular inverse of k modulo mode. So if mode is none, if mode is none, then default to the field modulo self dot p, and this is the check if there is k, if k is equal to 0, then throw the raise the uh, error message. So this is return power k minus 1 mod computes the modular inverse using Python's built-in function with the three arguments. This one is power, um, this is exponent, and this is mod. So this function def point add, this is the adding of 2 points. So uh, this function shows the addition of 2 points. So there are different scenarios. They are taken care in all this part of the code. So first scenario is that if the first point is at infinity, return the second point like 0, because it's on infinity, it's 0. So if p1 is none, return p2. Similarly, if p2 is none, it means it's in infinity, return p1. So x point 1 is open into its coordinates x1 and x2, and similarly point 2 is open into its coordinates x2 and y2. So if the points are inverse of each other, then there is a case. In this case is taken care of the inverse points. So in here, if the x coordinate are equal and y coordinate are not, the point are inverse. So and other case is doubling, if the point is same. So what happens, if the points are the same, use the point doubling formula. If the y coordinate is 0, the point is at infinity. Uh, Calculate the number for the slope here. So calculate the denominator, because this is numerator. We are calculating numerator here, and here we are calculating the denominator, and what numerator and denominator values will come on this step, we will put in this place to find the to calculate the slope. So else denominator, calculate the denominator for slope in other form, and then if denominator is equal to 0, return none. So okay, if 2 points are not same like this, otherwise the situation is taken care of here, that we will find numerator and denominator, and finally we will find its slope. So in this function, as we are multiply a point on the elliptic curve by a scalar k. So if a point is none, or k modulo self and dot n is equal to 0, if the point is at infinity, or k is a multiple of n, return none. And your k is within the range 0 to n minus 1. So here result is equal to none. Initialize the result as the point at infinity. Addend point, initialize the addend as the point to the multiplied. So here in the while loop, what we are doing, if the least significant bit of k is 1, add the current addend to the result. So addend dot self, addend is equal to self dot point add and addend, these are the arguments, and addend double the addend. So k, shift k right by 1 bit to process the next bit. So return the result. After the creation of signatures, this constructor function verifies a signature using ECC. So this all code is doing this to verifying the signature created in the earlier function. This code here and this is a compute the shared ECC points using ECDH key exchange. And this function here derive a shared key from the shared ECC point. Okay, this is our test.py file. After running the code, here are the results for this one. Okay, this is our test2.py file, and after running this, these are the results generated.